And I want to start by saying this is all joint work with Daniel Yang. Hi, I'm going to tell you about some of our work on the Hamiltonian locality testing problem. And I want to start by saying this is all joint work with Daniel Yang. Now, there's a lot of ways that you could think about what a Hamiltonian is, but we're going to, for the purposes of this talk, we're going to think about it in a kind of a computer sciencey way. So we're going to say that a Hamiltonian on n qubits describes how a quantum state on those qubits evolves over time. In particular, our Hamiltonians are going to be 2 to the m by 2 to the n dimensional Hermitian matrices, and evolving a state phi under one of these Hamiltonians for t time is going to mean sending phi to e to the minus iht times phi. And this unitary e to the minus iht is what we're going to refer to as the time evolution operator associated with the Hamiltonian H. So the question that we're interested in here is, suppose that there's some unknown Hamiltonian H that we can only interact with by applying this time evolution operator e to the minus iht, perhaps interleaved with whatever unitary, with whatever measurement at the end. What can you find out about H with this kind of access to it? And in particular, we're going to be interested in what you can find out about H using as little total evolution time as possible. That is to say, every time you apply this time evolution operator for a time t, we're going to bill you t time, and you're going to want to minimize the sum of these time intervals. So one thing you could try here is you could try learning H. You could try to find a complete description of it up to some error. Now, in general, this is going to be quite difficult. For one thing, even just writing down all of the parameters needed to describe an arbitrary H has exponential complexity. But maybe we don't really need to learn everything about H. Maybe we just want to know, does H have some property? And that brings us to the Hamiltonian property testing problem. First studied in this work of Bloom, Crowe, and Ufkir, where there's some property for which you want to determine whether H has that property, or whether it's at least epsilon far from every single other Hamiltonian that has that property. And in particular, the property that we're going to be interested in here is the property of locality. Can the Hamiltonian H be described exclusively by interactions between small sets of qubits? More formally, we say that a Hamiltonian is k-local if it can be written as a sum of these Hamiltonian terms, where each individual term acts on no more than k of the qubits and is the identity on every other qubit. Now, one reason to be interested in testing this is because many of the systems that we're interested in are ones that we expect to be local. And so a system being non-local is a sign that it is not behaving in the way that we expect. But another reason is that locality is a necessary precondition for a lot of the learning and simulation algorithms that we're interested in applying to Hamiltonians. So, like I said earlier, we're interested in minimizing the total amount of evolution time you need to solve one of these problems. And one interesting result coming from the previous work on this problem is that you can actually make this total evolution time completely independent of the size of the system that your Hamiltonian operates on. But system size isn't the only thing, the only parameter that you might care about. Remember that we're interested in differentiating between local Hamiltonians and Hamiltonians that are epsilon far from non-local. They have, like, say, an epsilon-sized non-local part. And you can imagine that this problem is going to get harder the smaller that epsilon is. For an extreme case, if you imagine differentiating between a local Hamiltonian or a local Hamiltonian with an asymptotically small amount of non-locality added to it, you would expect that to be extremely hard. And so what we want to know is, how does the required evolution time for this algorithm depend on this precision parameter epsilon? And what we've seen from previous work is that you can solve this in inverse cubic time. And the result that I'm going to tell you about here is that you can actually improve this to inverse quadratic time in epsilon. Moreover, it turns out you can actually prove that any algorithm would have to use at least inverse linear time. Now, I'm not going to talk much about that second result. I'll just briefly say that it comes from maybe the simplest locality distinguishing problem you could imagine, distinguishing the zero Hamiltonian that does absolutely nothing to the state that it acts on from a Hamiltonian that consists of a single epsilon-sized non-local term, say z's operating on the first through k plus 1th qubit. But what I do want to tell you about in the remainder of this talk is kind of an overview of where our improved performance comes from. And to tell you that, I need to start by telling you about the barrier that prevented previous work from doing better than 1 over epsilon cubes. But before I get there, it will be helpful, actually, to take a slight detour into talking about writing Hamiltonians in the n-fold-Pauli basis. So any Hamiltonian can be written in this basis, which consists of just writing it as a sum of what we'll call Pauli terms, where each of these Pauli terms consists of applying a number of these Pauli XYZ matrices to individual qubits among our n qubits, while applying the identity to every other qubit. So, for instance, this Hamiltonian here, acting on 2 qubits, can be written as the sum of the Pauli term z tensor I and the Pauli term x tensor x. Now, why am I telling you about this? Well, it's because writing Hamiltonians in this way is very convenient because it gives you this really nice definition of the distance of a Hamiltonian from locality. Every one of these Pauli terms is either local, which means that it just involves, say, fewer than k Pauli non-identity Pauli matrices being applied to the qubits, or it's non-local. It has more than k non-identity Pauli matrices being applied to the qubits. And that means, as it turns out, that you can write down the smallest distance from H to a non-local, the closest local Hamiltonian to H will be the Hamiltonian that just consists of all of the local terms in the Pauli expansion of H. And so the distance of H from that closest local Hamiltonian is just the size of the sum of all of the non-local Paulis in the Pauli expansion of H. And so you can actually estimate this distance from locality if you're able to figure out a way to sample from this Pauli spectrum of H, and thereby estimate the amount of mass on the non-local Pauli terms in the expansion of H. So how can you do this? Well, what you can do is you can exploit a nice property of just the tensor product of n Bell pairs. You see, it turns out that if you take this state, which I'll call sigma, and apply a Pauli term to half of it, by which I mean for each of these individual Bell pairs, you'll be treating the right qubit in that Bell pair as the one that you're applying the Hamiltonian to. So if you apply any I tensor P for any Pauli term to this tensor product of Bell pairs, you get an orthogonal state for any different Pauli term. And what this means is that if you could apply I tensor H to this state sigma, and then measure in the basis that differentiates applying all of these I tensor P's, you could sample from the Pauli spectrum of H. Now, it's not actually possible to do this directly, not least because I tensor H times sigma wouldn't even be an actual state. But what's been done in previous work is they've approximated being able to do this by exploiting the fact that the time evolution e to the minus iht is approximately I minus ith as long as t is small enough. This is just the first order approximation of the complex exponential. And so the algorithm that this gives you is that you choose some t small enough that this first order approximation of e to the minus iht holds well enough for your purposes. And then you measure I tensor e to the minus iht times sigma in a basis that differentiates I tensor p times sigma for each p. Each of those iterations lets you sample a term with some probability, and you repeat until you've estimated the weight on the non-local terms in your Hamiltonian H. Now, your probability of hitting a non-local term is going to be proportional to t times that non-local part of H, all squared, just because quantum measurement probabilities are given by squared amplitudes. And so keeping in mind that we're only trying to differentiate local Hamiltonians from ones with at least an epsilon size non-local part, that means that our probability of hitting a non-local term is going to be at least epsilon squared t squared. And so we'll need to repeat like 1 over epsilon squared t squared times. Each of these repeats costs us t because we're evolving for a time t. And so we have a 1 over epsilon squared t total cost for this algorithm. And what that tells you then is that the cost is actually determined by how large you can make t. The larger that you can make t, the smaller the total cost of the algorithm. So how large can you actually get away with making t? Or put it another way, how small a t is small enough for this first order approximation of the complex exponential to hold well enough for our purposes? Well, if you write out this first order approximation and then write out like that second order error term, that second order error term is going to look like t squared times the size of h. So we'll assume that h has been normalized so that its norm is like 1. And then that will tell you that t needs to be scaled by about epsilon in order to avoid the error term swamping this epsilon-sized non-local component of h. And so plugging t equals epsilon back into that 1 over t epsilon squared time complexity that we had on the previous slide, that tells you that this method is going to require inverse cubic time in epsilon. But of course, the thing that immediately comes to mind when you look at this calculation is like, can you somehow get away with making t bigger and thereby reduce the cost of this algorithm? And to answer that question, it'll be useful to start by just asking what goes wrong when we make t bigger. Well, the problem is that e to the minus iht, this complex exponential, has these h squared, h cubed, etc. terms that are going to become relevant when you start making your t large. And just narrowing in on that h squared term for a second, if we write this as the sum of its local and non-local part and then square it, you can see you end up with this h squared local term that could potentially look non-local, even if the actual non-local part of h is 0. To make this concrete, imagine that the local part of h is, say, a z operating on the first qubit, and then kz's operating from qubit 2 to k plus 1, so it's certainly k local. But then when you square it, you now have this z1 to zk plus 1 term, which is decidedly non-local, acting on k plus 1 qubits. So our approach in our algorithm is to suppress the local part of this time evolution using a procedure that we refer to as Trotterized postselection. And so the idea of this is that you start by evolving for just epsilon time. So you end up with like an epsilon h local part and epsilon h not local part applied to sigma. But then you measure with this projector pi, where pi projects onto I tensor p times sigma for every local Hamiltonian term p, and then we post-select on not getting the pi result. Then, when you apply, if you do not fail the post-selection, you've effectively projected by I minus pi, and so the resulting state just has the non-local part of the evolution of h. And so if we repeat 1 over epsilon times, and we're fortunate enough to never fail the post-selection, what we'll end up doing is we'll kind of approximate applying the time evolution of the non-local part of h for a constant amount of time. Unfortunately, it turns out that our chance of failing post-selection is actually pretty small. At each instance, our measurement is only looking for an epsilon-sized local part of the evolution, because we only evolved for time epsilon. So we'll only have an epsilon squared chance of hitting that. And so even with our 1 over epsilon repetitions, we'll still only have an O of epsilon chance of failing post-selection. And if we don't, we get to measure something that has a linear amount of non-local evolution of the non-local evolution applied to our starting state sigma, and will detect non-locality with probability proportional to the square of the non-local part, which again we get to assume is at least epsilon squared, because we're just trying to differentiate whether something is epsilon far from being local. And so that gets us our result. We only have to repeat 1 over epsilon squared time, each paying a constant amount of evolution time in order to detect non-locality. And so that tells you that there is an algorithm that solves Hamiltonian locality testing using only O of 1 over epsilon squared evolution time. Now, the natural open question here, of course, is can you close the bound, the gap between these upper and lower bounds? And I personally think that the O of 1 over epsilon squared bound is probably the correct one. But one wrinkle that comes up if you want to try and prove that is that we know that if you were able to run the time evolution of the Hamiltonian in reverse, in other words, you had access to the inverse of the time evolution operator of that Hamiltonian, you would actually be able to get an O of 1 over epsilon algorithm using quantum amplitude estimation. And if I was giving this talk a couple months ago, I would say that this was a really big barrier to proving that 1 over epsilon squared was the correct evolution time, because it would necessarily imply that quantum amplitude estimation required the inverse, which had been an open problem for quite a long time. But just this year, there was this exciting result by Ewan Tang and John Wright showing that you really do need access to the inverse if you want to do quantum amplitude estimation. And so that, to me, kind of suggests that maybe you could get this lower bound up to 1 over epsilon squared by using some of the techniques that they use to prove the hardness of QAE. Another question is whether you actually need these ancilla qubits we used. Because remember, we were preparing a 2n qubit state and only applying h to half of it. But there is other work on the problem that doesn't achieve 1 over epsilon squared, but that doesn't use any ancilla qubits. So a natural question would be, can you combine these techniques together to get 1 over epsilon squared without ancillas? And finally, you could also ask about the query count needed for solving this problem. That is, the number of times you have to apply the Hamiltonian time evolution operator, rather than the total amount of time you have to apply it for. Keeping in mind that, at least in general, you might expect that applying the time evolution operator many times for a very short amount of time is more expensive than applying it for, say, one large block of time. And so that's all that I wanted to say about this problem. Thank you for listening.
Thank you so much, John. So, any questions for the speaker? He's live with us to answer your questions.
Thank you for the talk. This is to ask you, instead of post selection, if I had done some filtering operation, do you think it would improve, or do you think you will get different results? Filtering operation is something like some non-invertible operations, L dagger. Simply I do it, it will be probabilistic. Instead of a two element post selection, why not we do filtering operation?
Yeah, I'm not sure I entirely understand what you mean by by a filtering operation as opposed to post-selection in this context.
Okay, on a qubit, if I have a qubit state, I would use a invertible matrix, A row, A dagger. So then whatever is the result, if I apply A, so it will be A row, A dagger with probability being trace of that A row, A dagger. So that is any invertible operation will do. So for that kind of a purpose. So this is just a thought because filtering operations have been employed in several cases and that shows some improvement. So I am posing this question.
So let me see if I understand. So, are you suggesting using, sorry, like an invertible operation that would take the local the the basis elements corresponding to sigma with I
Right.
tensor some local
Right.
p applied, and then take them to, like, say, some like junk state that
Sure.
you don't care about. Let's see. So I think off the top of my head that should work and should end up having similar asymptotics, but and end up, sorry, having the same asymptotics, but
Okay. Thank you.
I'd have to think if I was missing something.
Thank you.
So
Uh, Hi, John. Thank you for the talk. I might be missing something, but I did not see any dependence on number of terms in the Pauli decomposition of the Hamiltonian. Does
yeah,
it
that's
not?
right.
Does it not matter, or?
Yeah, it's there's no dependence on the sparsity or otherwise of the Hamiltonian, or on the number of qubit, or any dependence on the system size. I mean, there's, if you can think implicit dependence in that you're operating on n qubits, but beyond that, no.
Okay. Thank you.
Hi, thanks for the talk. I have something that sounds almost exactly the question. So maybe you can comment on this. So is it fair to think of the testing problem you're solving as the quantum equivalent of like K-Runta testing, but somehow not only do you not have a dependence on N, but also not on K there?
So so K-Hunter testing would be would be a different problem in the So you can imagine that the Hamiltonian version of K-Hunter testing would be saying something like, right, there's like a secret subset of the qubits which such that all of the Pauli terms lie in that subset. Whereas locality testing is saying so the classical equivalent of locality testing is asking, like, do all of, like, for, say, a Boolean function, do all of the Fourier terms act are they all degree at most k? And in fact, you can that if you consider, if you have like a Boolean function and you allow yourself to do fractional queries, that literally is Hamiltonian locality testing, except for Hamiltonians that are required to only be supported on the Z basis. I don't know if that answers the question.